How can artificial intelligence invent entirely new cooking techniques by combining physics principles with creative computational search? This lecture explores how artificial intelligence systems can discover novel cooking methods by systematically exploring the intersection of thermodynamics, fluid mechanics, and material science. Let us begin by conceptualizing cooking as a multidimensional optimization problem in a vast parameter space. Each cooking method occupies a point in this high-dimensional space, defined by temperature profiles, time sequences, moisture content, pressure variations, and chemical environment. We can express any cooking method M as a function of temperature T, pressure P, humidity H, and chemical composition C, all evolving over time T. Before we proceed, let us ask a fundamental question. What constitutes an optimal cooking technique? An optimal technique satisfies multiple competing objectives, achieving a crispy exterior through Maillard reactions, maintaining a juicy interior by preventing excessive protein denaturation, minimizing oil usage for health considerations, and completing in reasonable time. We construct an objective function J that balances these competing goals, with weights W reflecting our preferences. This is a multi-objective optimization problem. The foundation of computational cooking design rests on understanding heat transfer mechanisms at multiple scales. Heat flows into food through three mechanisms: conduction through direct contact, convection via fluid motion, and radiation from hot surfaces. The AI must model all three simultaneously. The heat diffusion equation governs temperature evolution, where alpha is thermal diffusivity, Q represents heat generation from reactions, C_P is specific heat, and ρ is density. Temperature gradients develop across the food material. The surface reaches high temperatures rapidly while the core lags behind, creating the fundamental challenge of cooking. Let us perform a quick scaling analysis to understand cooking time dependencies. Cooking time scales as the square of the characteristic length L divided by thermal diffusivity alpha. This is why doubling food thickness quadruples cooking time. For a chicken breast of 1 centimeter thickness cooking in time T, doubling the thickness to 2 centimeters requires 4 times the duration, not twice. This quadratic scaling is fundamental. Using typical meat thermal diffusivity of 1.4 times 10 to the minus 7 meters squared per second, we can predict cooking times accurately. Surface browning through Maillard reactions imposes critical temperature and time constraints that AI must respect. Maillard reactions proceed negligibly below 140 degrees Celsius, but accelerate exponentially above this threshold. The AI must ensure surface temperatures exceed this critical point. The reaction rate follows Arrhenius kinetics, exponentially dependent on temperature T, with activation energy E underscore A around 100 kilojoules per mole and gas constant R. The ideal temperature profile shows a hot surface at 180 degrees for browning, intermediate layers around 100 degrees for moisture retention, and a core at 65 degrees for optimal protein texture. Let us consider why conventional deep frying struggles to achieve these competing objectives simultaneously. In deep frying, the uniform high-temperature oil creates excessive heat flux, driving rapid moisture evaporation from all surfaces. This produces crispy exterior, but risks drying the interior. Moisture flux J is proportional to the moisture gradient with diffusion coefficient D. High surface temperatures create steep gradients driving water loss. Now we examine how AI systematically explores the space of possible cooking methods to discover superior techniques. The AI employs a tree search algorithm where each node represents a cooking state defined by current temperature distribution, moisture content, and chemical composition. Edges represent actions like temperature changes or time increments. Using reinforcement learning, the AI learns a Q-function mapping state-action pairs to expected cumulative reward, with discount factor gamma for future rewards. The search space includes traditional methods like steaming, boiling, and frying, but also novel sequences combining these primitives in unconventional ways. The first AI-discovered technique involves a two-stage process: initial steaming, followed by rapid high-temperature searing. Stage 1. Steam the food at 100 degrees Celsius to gently and uniformly cook the interior without moisture loss. Stage 2. Brief high-temperature sear at 250 degrees to rapidly develop surface browning. The steaming duration follows from the heat equation solution, where T_0 is initial temperature, T_C is target core temperature, and T_ENV is steam temperature. The temperature profile shows gradual core heating during steaming, then a transition point marked by the vertical line, followed by rapid surface temperature spike during searing while core remains stable. This method achieves both objectives. The steaming phase preserves moisture by operating at water's boiling point, while the brief sear develops Maillard products without significant additional water loss. Water mass loss is proportional to the duration at high temperature times the moisture gradient. Minimizing high temperature exposure minimizes moisture loss. Let us quantify the oil reduction achieved by this steam sear method compared to traditional deep frying. Oil absorbed during deep frying equals oil density times surface area A times penetration depth delta, typically around 1 millimeter for fried foods. Brief searing with minimal oil contact reduces penetration depth by approximately tenfold, yielding a 90% reduction in oil absorption. Visual comparison. Deep frying uses 10 times more oil than steam searing for equivalent surface development. This is a substantial health and cost benefit. The second AI innovation involves precisely controlled partial dehydration to achieve crispness without cooking. The method uses low-temperature air at 50 degrees Celsius with controlled low relative humidity of 20% to gradually remove surface moisture without cooking the interior. Evaporative flux depends on mass transfer coefficient H_m and the vapor pressure difference between the surface at saturation P_sat and the ambient air adjusted for relative humidity RH. Surface moisture content decays exponentially during controlled dehydration. The optimal stopping point, marked in red, achieves crispness threshold without over-drying. One might ask, why not simply use a conventional oven for this dehydration? The answer lies in precise control. Conventional ovens create temperature non-uniformities and cannot precisely control humidity. The AI method uses sensors and feedback to maintain exact conditions, preventing localized over-drying. Ideal crispness requires surface moisture fraction below 0.1, while maintaining core temperature below 60 degrees Celsius to prevent protein denaturation. The third innovation involves marinades engineered to undergo controlled phase transitions during cooking. The marinade contains a precisely formulated salt-sugar eutectic mixture that melts at a specific temperature, creating a protective liquid layer that moderates heat flux. The eutectic melting point depression follows the freezing point depression equation, where K is the cryoscopic constant and X is the mole fraction of solute. The heat absorption profile shows a plateau during the phase transition, where energy goes into melting rather than raising temperature. This buffers the food surface from overheating. The latent heat absorbed equals the mass of marinade M times the latent heat of fusion L_F, typically around 200 kilojoules per kilogram for salt-sugar mixtures. Let us estimate how long this phase change marinade can buffer surface temperature during high heat cooking. Buffering duration equals marinade mass times latent heat divided by incoming heat flux, Q_in from the cooking environment. For oil at 200 degrees and melting point at 80 degrees, with convection coefficient H of 100 watts per meter squared Kelvin, heat flux is approximately 10 kilowatts per meter squared. A 1-gram marinade layer provides approximately 20 seconds of thermal protection, sufficient for rapid searing without interior overcooking. Visual comparison of moisture retention. Without marinade, successive layers show decreasing moisture indicated by decreasing bar height. With phase change marinade, moisture retention is uniform across all layers. The AI can combine these discoveries into an integrated multi-stage cooking protocol that outperforms any single method. The method starts with phase change marinade, followed by controlled dehydration, and finishes with steam searing. Each stage leverages discoveries from the AI's exploration of cooking physics.